Chapter 8, Pearson, Basic Chemistry. We're going to look at equations for chemical reactions over and over again. Balancing a chemical equation over and over again. Types of reactions over and over again. Oxidation and reduction. A little less formally, but it's throughout all these chemical reactions. You're going to see it happening. Okay? So we're going to talk about formally in some ways, but you're going to see evidence of it throughout it. So here we go. And we will plan on a work session to work through these in more detail. All right? All right, a chemical change occurs when a substance is converted into one or more new substance. That's a chemical change. When it's converted into one or more new substance, we have experienced a chemical change. When silver tarnishes, silver metals reacts with sulfur to turn it black substance, we get what's this? Silver sulfide. We don't have to tell how many, right? Because silver's, you get it? Metal and a non-metal. Same thing with the green roofs that you see around. Yeah, they start off kind of orange and they turn green over time. All right? That's what's happening. All chemical change, the leaves on the tree. These are other examples here of chemical changes and chemical reactions. All right? If you cook it, it's definitely going to be a chemical reaction. If you burn it, it's a chemical reaction. All right? And when the chemical reaction happens, the composition changes. It's not the old composition anymore, it's a new composition. You start with the material that you're baking. First you have the sugar, the flour, or the whatever, the nutmeg or vanilla flavor or whatever you put in this cake or these cookies, and you put them together, and voila, it bakes, it expands, blows up because it's blowing off CO2 gas, and you get this nice cake. The only thing that doesn't happen is raisins should always still come out raisins. You're a terrible cook if your raisins change, okay? There's something wrong with you if you come out with raisins. Yeah, that's first. If someone gives me a cake with raisins in it, I see whether they change. If they change, I'm walking away, man. I'm telling you, okay? But everything else, there should be a chemical reaction, all right? And if the raisin changed, there really was one. That's too much baking. All right, we got it? So when charcoal is burned on the grill, the carbon in the charcoal combines with oxygen and water and air to form water and CO2 gas. That's what's happening on your grill. You're generating CO2, which is the same thing you exhale when you breathe. Right? You got it? Did I say that right? Yeah. Every chemical reaction is written as a balanced equation. It is critical that the first step you do, write this down, put it on a post-it, take it on a date, put it on a stop sign, do something. You must first check to confirm that your reactions are balanced. So before you do any problems, any questions in this class, check to see if they're balanced. Don't trust me that I remember to tell you it's balanced or not balanced. So everyone follow. That is step one in these chapters. Is the chemical reaction equation balanced? If your chemical equation is not balanced, you cannot get the right answers. Got it? So that is important. Now, nature does it. It does it naturally when you do it. Okay? Just so we're trying to figure out how to do it, so we have to write it down. And we do that by counting the number of atoms on each side of the equation. Let's disregard the blue twos for now. Without the blue twos, we have two hydrogens. Does everyone understand that's two? We've gone over this before. And over here we have two. Over here we have what? Two oxygen and one oxygen. So you play a shell game with this, and you put numbers in front of it until it balances it out. Okay? So everyone follow. Okay? That's what you do. You do the multiplication. You do not change the numbers at the bottom. Got it? It's the coefficients in front to balance the equation. And so you simply do that. Now, for some people, you'll do that intuitively. And it'll drive you nuts to wait on everybody else to count them. You'll just see it, and you'll write it, and you'll go, that's okay, that's absolutely fine. I once had one kid that I could not come up with a problem that he could not spot inside. He'd stare at it, bam, boom. And I tried some of the hardest problems I could. He just could intuitively see it. Okay? I do not test you on how you balanced it. I just care that it's balanced. If you have to write down every element down the side of your paper to get it done, fine. I won't care what I see there. All I'll care about is when I look at this equation that it's balanced. Does everyone follow? Be aware of that. You get no brownie points for how you got there. 0. If it takes you 2 hours to get there, tough. Got it? It's the balancing of it. Some will do it intuitively. Some will sit down, they'll write them each out. They'll count them. They'll do some tallies. They'll do some math. There's a math approach to doing it, and then there's an intuitive way of doing it. And I don't care which one you do. So what I'm not going to do is teach you an ideal way. You're going to watch us balancing equations and pick up some tips on how to balance. So everyone follow. But if you can intuitively see it and do it, we're good. All right? So we have to have these balanced equation coefficients. These balanced equation coefficients are used for conversion factors. Note that. These coefficients are used for conversion factors. These coefficients are used for conversion factors. So a question for you. If I use these coefficients as conversion factors, should I count them in my sig figs? No. Never count your conversion factors in sig figs. These are universal. Got it? Be aware of that. On the left side, we have the reactants. On the right side, we have the products. That's it. That's straightforward. Reactants, products, reactants, products. And it must be a balanced equation. The balanced equation coefficients are used as conversion factors. Here, this author shows you a picture of what it looks like. When you have hydrogen, you have oxygen, it combines. You count it all up. You have 4 white ones, 2 red ones, in a balanced equation. Therefore, it's balanced. You can do it this way. You can do it any way you want to do it, as long as it's balanced. I am not going to ask you to prove to me how you balanced. Okay? Solution. How it happens here. This shows you one way of doing it. You have P4. You write out 4 P's. Does everyone see that? 4 P's here. 12, 12. I don't think I'm going to beat this drum any harder than that, unless someone needs me to. We're all good? This is counting. Yes.
So I know this is probably, I don't know. What is the indicative of the parentheses? What is that?
Yeah, it's a good question. For this, I'll comment on them as we go. Yeah, it starts with solid, liquid, gas. And this author is making a point of showing you the state of each of the elements that you used. To balance an equation, that won't matter. So occasionally I'll forget to mention to you solid, liquid, gas, because of the nature of this class. So he is showing you, he chooses to show you, and he shows it throughout. Follow? You'll see occasionally when I give you the solution, when I write them out, you'll see that sometimes I'll write fast and I'll leave out those, so I'm moving fast. I try to make sure that I put them in because this author uses them. Some authors don't use them.
Really pertinent to what we're doing.
To what you're doing. That's correct.
So if we don't put them down like on our exam,
you're not going to lose. You're not going to lose points on that.
thank you.
Yeah.
Beautiful.
Yeah. It's his that he prefers to do that.
Because I can lose enough points on my own. I mean, I don't need to add that.
You don't need that too. Yeah, I hear you. Yeah, I got you. Yeah. No. These. I won't be. I'll mention these. I will talk about why it's important. But in terms of balancing the equation and solving the problems that we have to solve to teach you the concepts, we won't go into the details on this. That's another level up. Okay. Thanks. Good to point that out, though. All right. So we're seeing this just shows you that the state, and why is he showing you? The reason he's showing you that he shows you that it's changing. His emphasis here is the changes. In this particular case, you see you have the solid and the liquid that goes completely to a what? Gas. This is the point that he's emphasizing. We know the physical properties also changed. That is the emphasis of the solid, liquid, gas. It is to show you that not only that the atoms recombine, but the physical state of those atoms recombine. And in fact, you could use, if you could erase the elements, and you could say I have a solid plus a liquid and I got a gas. Anything happen, the answer would be what? Yes. Right? Because you start with solid, liquid, you have a gas, therefore chemistry must have occurred. That is the emphasis that he's making on this. Here we show you another way we balance it again. And there are tricks to do. I suggest to you, you can make a note of this. now, and we'll talk about it and go through it later, but just so you can know when you're trying to play with it at home. It's if you start with the element that has more attachments and appears to be a larger element, start balancing it first. The others have a way of working themselves out. Don't start with something like oxygen and water and hydrogen. Do them last. Okay? Now you can start with them, but it gets easier more time not when you balance out, say, like the metal, like this. You notice this is Fe2O3. I would start here instead of aluminum because it's standing alone. Do the standalones last. So I would start with balancing iron first. Then I would see if everything else works itself out. Got it? So that's just a way of starting. You can start any way you wish, but that's just a quick way of working through fastly. Okay? So we write the balance equation here. Let's see what we have. We have CH4 plus 2 oxygens. This is combustion. Combustion always has oxygen and it generates water and CO2. You'll always know that's combustion. Complete combustion generates carbon dioxide. Incomplete combustion generates carbon monoxide, which is the silent killer, poisonous gas, which is what happens when you don't stoke your fire well. You get carbon monoxide, builds up in the cabin. That's why if you're up in your cabin, you want to open your windows occasionally. I don't care how cold it is. Open your windows. If you're running a wood stove, that kind of thing. Okay? It's really smart. Just occasionally air out the place. All right, so here we have it. We balance is not balanced. You count them through. You determine it's not balanced, right? Because somewhere we can count them and see, right? Right away, we see 4 hydrogens and 2 hydrogens is not balanced. So I'm going to balance. My carbons are good, so I'm going to put a 2 in front of here and see if that balances it out. It gives me 4, 4, 1, 2, 2. Did everyone see what I just did? No, it gives me, so I need to put a 2 here now, right? That gives it 4. So it's going to be a 2 here and a 2 here. Okay? There is no magic to this. You just have to do it till you figure out your best way to view it. And again, I have one kid, I could put it up, and in a few seconds, he could just do it. He just could intuitively see it. Okay? He never missed a balanced equation. He caused trouble for the rest of the class. It was upper level class, because I was trying to find one equation this kid couldn't balance. I couldn't. He's just that good. He was good. So here you have it. So we'll follow. This is a balanced equation. We're going to practice these. Okay? And you'll need to play with them a lot. I'll post some practice ones for you. These we have to memorize. These are the chemical reactions. They're classified this way. This is their name. You have to memorize them. Some authors use slightly different names. We're going to stick with the names that are in this book. Okay, does everyone follow? But they all mean the same. They're synonyms. And each author kind of uses a slightly different variation of synonyms. You will have to memorize these. We're going to show you what they look like, and we're going to give you some tips on how to ID them. Okay? And that's all we're doing. We can only give you tips about memorizing things. You follow? So here we go. These are the reactions. I think they should come up. Combination does exactly as a combo. It's going to take 2 and go to 1. You got it? It's going to be a combo. 2 going to 1. If the 2 goes to 1, it's a combination. Some authors use the word synthesis, but then some argue that synthesis is everything in the world. Okay? So if you see that term, this is what they're talking about, combo. It's combination. Okay? Does everyone follow? So there you have it. Not much else you can say about that. We simply have to do what? Memorize it. That when we see 2 going to 1, it's a combo. All right? And that's just what they chose to name. In this particular case, is this one balanced, by the way? Yes. 2 mags, 2 mags, 2 oxygen, 2 oxygens. Everyone see why I say 2 oxygens here? Anyone doesn't see that? 2 times the 1 oxygen gives me 2 here, and there's 2 here. Take a look at this one. N2H2, is it balanced? Yet this is, nope, it's not. We're not balanced here, are we? That's 6, so we need to put a what?
2.
A 2 here?
Yeah.
And that'll make it balance out?
Yeah.
Cool. Got it? All right, everybody see that? All right, here, a decomposition is exactly that. One going, it's the opposite of a combo. 1 going to 2. Decompose it, it falls apart. Okay? Now, occasionally over this arrow, you'll see things, oh, here it is, heat or something that causes it to decompose. We don't count heat as part of it. Neither do we count catalyst as part of it, and you'll learn why later. Okay? All right? So it decomposes. Here, it decomposes. Did we get the right numbers, though? 2 and 2. Balance. Did we balance this one? 6. 6. We're good? There you go. It has to be balanced. And in this particular case, look at this decomposition here. It went from a solid to what? A liquid and a gas. In this particular one, went from solid to a solid and a gas. Okay? The physical state, the chemistry changed, the chemical composition changed, and so did the physical state change. As the physical state changed and the physical properties changed. Single replacement. And you'll have to find your own little trick for doing this, okay? But one way to look at a single displacement, you'll see one thing, they exchange partners. It's like a do-si-do. Exchange its partner, kicks this one out, bam, it's gone. Okay? But here, what kicks it out, there we go. All right? Okay? So here we have zinc, here, and now hydrogen's gone. It's been kicked out. Okay? Here we have iron, and notice copper is kicked out. I want to also notice something here we mentioned before. Chemistry is written by electropositive followed by electronegative. That's how we write chemical compounds, electropositive, electronegative. So as soon as you see any chemical composition, you know the first part is positive, the next part is negative. That's how we write them by convention. That's it. That is the standard. Okay? And notice here what happened here with this iron. We know iron likes to be what? Positive because of where it's located on the periodic table. So it's going to exchange with copper, which likes to be positive. You get it? So you just take a look at those things and looking at the periodic table. Here, zinc likes to be positive and hydrogen does as well. They're going to exchange and they're going to kick it out. In doing this, there's also going to be oxidation and reduction, which means oxidation means we're going to lose some electrons from one species. Reduction means we're going to gain electrons. And the way you know that is oxidation becomes more positive. Reduction becomes more negative. Okay? All right, you'll have your own ways of remembering that, but that's how I tend to talk about it. So oxidation becomes more positive, okay, and reduction becomes more negative. Notice here, zinc in this case has a 0. Note this. Any element standing alone has a 0 charge. If it's an element, if it's in an elemental state, it has a 0 charge. Everything on the periodic table has a 0 charge. Got it? When it stands alone, it's a 0 charge. When it combines with something, it either becomes oxidized or reduced, which means that within its composition, it has a charge. In the case of zinc, this is +2. So zinc went from 0 to +2. It was oxidized, became more positive. In this case, chlorine here has a -1. You know that because you looked at the periodic table, did you not? Right. Chlorine is located in what? 17. Its typical charge would be then a what? -1. Okay? You will be tested on some of this too, by the way. -1. And here it went, and it remained a -1. But on the other hand, hydrogen went from a +1 to a 0. You know a 0 because it's standing alone. It's in its elemental state. Does everyone follow that? So I would certainly expect you right off the top to be able to identify the charges on standalone elements, because that charge on standalone elements is what? 0. Does everyone follow that? Hydrogen 0, copper 0, iron 0, zinc 0. If it's on the periodic table, its charge is 0. So that's your single displacement. So that's a single. Now we're just do-si-do here. You get it? So everybody changes partners here. So you have 2 and 2 going to 2 and 2. In this particular case, you have 1 and 2 going to 2 and 1. Follow? You simply have to memorize those. So not much else we can say about that other than memorizing. And that's just what we call it. Then combustion is always oxygen, air, something to give you oxygen. And it produces carbon dioxide and water, or carbon monoxide and water when you're at a campfire and you don't stoke the fire. You get incomplete combustion. Okay? Or when your vehicle isn't operating properly, you didn't get a tune-up or whatever. Okay? So here we show you examples of combustion reaction. Is it balanced? That's the first thing you want to always ask yourself. Even if you look at it, you want to check it. You get in the habit. We have what, 20, what's this? How many oxygens here?
26.
And you guys agree it's 26, and you know why it's 26? Does everyone know why it's 26?
13 times 2.
Thank you. Then we're good. So we can move with this then. So now you see all the rest of them should be balanced out here. 8, 20, and what's that, 16. Did I get this right over here? Oh, we got more over here, don't we? How many is this? 26? 36? Yeah. Everybody follow 30? No, it's not. No oxygen there. It's only 26. See, I can't even see. You know, I can't even see this far. This is bad. I should wear binoculars and get it over with. This is 26 oxygen. So how many do I have over here?
16
and 10. So we're good. Okay. You guys can count better than I can because you can see, fortunately. Butane burns. Basically, it combusts. That is the bottom line. Does everyone follow? Here, show you all these reactions on one slide. No magic here. What is it? Memorization, folks. You have to memorize the names. All right. Here it shows you some examples. Let's see if we can do these. Ready? Anybody want to take a shot? It's balanced, by the way. What is this one? Combo. Yeah, combo. 2 going to 1. Right? All right, what about this one? Single, right? So you want to see why single? You have 1. All right. What about this one? Double. Yep. And what about this one? I'm sorry?
Decomposition.
Decomposition. Yeah. Yep. You get it? So you just simply look at it and you name it. It's like naming your kids or naming your pets or naming your favorite car, having clothes. Okay? So you simply name it. And these are the names. Rust forms when oxygen and air react with iron. That's rust. Oxidation. Okay? Most people have heard of oxidation and thought of oxidation. So let's talk about it for a little bit here. Okay? In an oxidation reaction, we call it redox. Electrons are transferred from one substance to another. I expect you to know that. Redox involves electrons transferring. Okay? All right? And so that's how we get it. If one substance loses an electron, another substance must gain electrons. You can't have oxidation without reduction. If you have oxidation, then there must be reduction somewhere. They come together all the time. That's how they operate. And here we show you an example here. This electron is oxidized because it loses an electron. Remember, electrons are negative. So if it loses negative, it becomes more positive. You got it? All right? So it loses oxidized. That means it's shifting to the right side. If you face the periodic table, it's shifting to the left side of the periodic table, trying to get back to the noble gases. So this gains an electron. It's a great. Okay? I'm shifting to the right, trying to move to the noble gases. So you have oxidation going to the left side of the periodic table, reduction going to the right side. Okay? It's becoming, when it becomes positive, it's becoming an isoelectronic with something to the left, and the other is becoming isoelectronic with something to the right of it. And so here we show it. Now, since this is oxidized, it is the reducing agent. It sends the electron away. Since this is reduced, it is the oxidizing agent. Okay? And you want to get used to talking about that. So you want to read your text and look at that. Okay? Oxidation defines a loss of electrons, reduction is a gain of electrons. That is the definition we expect you to know. One way to remember it, this is his way of remembering it. Okay? Now, most most authors don't put their memorization tools in their books, and this author, for the most part, doesn't do that. But he couldn't resist it here. We all sneak one in somewhere when we publish. Okay, it's just the nature. It's in the nature. We all have a pet peeve that we really thought of, and nobody else in the world thought of it, so we have to sneak it in. You can memorize it this way if you wish. Whatever your way of memorizing, I'm not going to ask you this. Does everyone follow? But I do expect you to know the definition. How you memorize it is up to you. Atoms of metals lose electrons to form positive ions. On the periodic table, metals like to go to the left side of the periodic table to become noble. They like to lose electrons, become more positive. Non-metals gain electrons, become more negative. Starting 14, group 14, 16, 17, 14, 15, 16, 17, they like to gain electrons, move to the right side of the periodic table to become noble. But 1 through 13 like to become positive and move to the left. The green color appears on copper surfaces weathering, known as Butane, is a mixture of copper carbonate and copper oxide. Okay, this is copper carbonate, right? Because it is a what? It's a transition metal, right? And you actually should, by nature, tell which charge it has. Which charge does it have? 2. Does everyone follow? Copper 2. Does everyone follow? Okay. We know it has 2 because you know carbonate has a -2. You memorize that. You also know that oxygen has a -2 because of where it is on the periodic table. And there are no subs at the bottom, which means copper must be a +2. Everyone see how we did that? So here we show you how to balance these oxidation reactions, and we balance them in this way. Oxidation-reduction reactions take place when copper metal reacts with oxygen in air, and this is an example, and the same thing happens. So we have copper that goes to copper +2, but this balances out with a 2 in front of it. Okay? So since it's 2 here, it must be electronically neutral, therefore you need 4 electrons. Does everyone follow that? Okay? Copper, 2 electrons. Everyone kind of see that maybe? It's the math. Copper likes to lose 2 electrons per copper atom. So if I have 2 copper atoms, how many electrons do I lose? 4. Everything that's always balanced. You have to always count it. Okay, and it has to have some rationale, okay, that's scientifically valid. Here we have oxygen. The reason this happens is because oxygen kind of dictated it, because I have 2 units of oxygen when I go back to my, there's the balance equation. So when I look at my balance equation, this is what happens. Follow? And so here, this dictates the number of electrons that have to move to balance the equation. So the bottom line here is not only does the atom count balance, but the electrons balance as well. That is the take-home point we're making here. Okay? Does everyone follow? Okay? Atom count must balance and the electron count must balance. So here we show you some examples here. Sodium, oxidation, lose an electron. Calcium, 2 electrons. Does everyone see why 2? It takes 2 to go back to noble. Count on the periodic table again. Don't try to memorize this stuff. Just look at the periodic table wherever calcium is. 1, 2. Okay? All right? This is for bromine. It wants to reduce. It wants to gain 2 electrons because it's Br2. What's the natural state of bromine? Not Br. It's what? Br2. It is diatomic in its natural state. We talked about that, I think, almost the first lecture. And so, therefore, we need to do 2 electrons. In case of iron here, iron plus 3 likes to go to iron plus 2. That's as far as it likes to go. Well, actually, that's not true. It can make it to 0. So here, we have iron plus 2, 1 electron, and we gain. And so we expect you to be able to count electrons and count how many there. We expect to be able to look at the periodic table and have an idea of the charges. It's very likely if the D groups, the D block, I'll give you big hints as to what those are. But I do expect you to know the S block and the P block. Okay? I expect you to be able to look at the periodic table and know that group 1 is 1 electron, group 2 is 2 electrons, group 13 is 3 electrons, group 14 is 4, group 16 is 3, group 16 is 2, group 17 is 1, etc. And that's basically counting blocks to nobility, to group 18. Follow? Simply count the blocks. Don't memorize it. But if you like to memorize it, that's up to you. Here it shows you a very practical life example of why this is so important. Okay, and why it's not boring to people like me. Because it's life. Life uses oxidation and reduction, and this is what doctors are often checking many times when they're checking your electrolytes and all these kinds of things, and they're going through all these and they're saying, well, yeah, boy, the electrolytic balance is off, etc. It's like your car battery. Okay? And you wonder why in the world they're checking this. This is what they're looking for. They're looking for these cycles to see if they're firing properly. If not, you have to put something in there to get it back, jump start it. In your car, in case you put sulfuric acid in the battery, you're good to go, but eventually it goes away if you don't take care of the rest of it. Okay, so here we have a biological example. Hint, hint, I would really look at this slide a lot. This is a slide I would look at a lot. I love to ask this question a lot. Things related to this slide I enjoy asking. Yeah, I've already written the exam. It's on there. Okay, all right. We have what? In this case, we have 2 hydrogens in a biological molecule. So there are 2 hydrogens. Let me make a statement before I go through this. One way to think about reduction and oxidation, particularly in a biological system. Reduction in a biological system adds hydrogens or removes oxygens. Okay? All right, in a biological system. Reduction will add hydrogens or it will remove oxygens. And so you can often simply look at the atoms, the count, and you say, did it add hydrogens? Yes. Therefore, it was reduced. Did it lose oxygens? Yes. Therefore, it was reduced. Follow? Okay, that's what. So you simply, and that's what you're going to learn. You're going to simply count the atoms. And so I just said oxidation, right? And then reduction. I would start reduction. Reduction. So oxidation is the opposite. Oxidation, you lose hydrogens or you add oxygen. So it's just the opposite. Okay. But I always like to start with reduction because that's a real key mechanism. So here, in this case, oxygen. Okay, in this case, we have a biological molecule that has 2 hydrogens on it. Boy, that could be a lot of them, right? A lot of biological molecules have 2 hydrogens. And we have this coenzyme, FAD. Because you can't have oxidation without reduction, right? What kind of reaction is this, by the way? What family of reactions is this? All right, so here we have the biological molecule with 2 hydrogens on it, and we have this coenzyme. It undergoes oxidation-reduction. This gets oxidized, which means there's going to be less hydrogens on it since it's oxidized. And this gets reduced, therefore it's going to have what? More hydrogens on it since it's reduced. You get it? Now, we said double a single displacement, only by way to force you to think about atoms moving around. But this is your classical redox reaction. You get it? I want to force you to think and look at this a little bit. You got it? And talk about, well, maybe it's this, maybe it's that. Why? Why not? You get it? And then you make a decision and say, well, wait a minute, this is classical redox. It's a classical redox, but you have to go back now which category it fits in, right? This is classical, and this is what happens in biological systems. The oxidation of a typical biological molecule can involve transfer of 2 hydrogen atoms, okay? This, or 2 electrons, 2 hydrogen, ion acceptor, such as coenzyme FAD, which you must have. Coenzyme is reduced, And so sometimes your coenzyme is off, or your enzyme, they'll say, well, they'll just say enzymes are off, or they talk about the enzymes. This is what they're talking about, and this is why they take a look at it. So they don't always tell you what type of enzyme, exactly what it is, and sometimes they talk about your coenzymes. And if you really talk to the doctors and you press them, you'll ask, well, we're talking about enzymes in general, and so we're talking about the coenzymes, and we're talking about this one, etc. And this is what happened. Your oxidation-reduction isn't firing properly, and therefore you're off a little bit. There you go, folks. You survive Chapter 8.